Hello. Let's check. Hello. Hello. Okay. Okay. I'm sorry. I with this kind of international research funding, I have to travel to Professor Patty French Sensor Lab in Tilburg, Netherlands. So that I'm now in Tilburg, and Tilburg is one of leading engineering research university in I think in Netherlands. They have their own this kind of cleaning facility and have a good collaboration with like NXP, right? And some of the sensor and even IMAC. So I also will visit IMAC, which is one of unique this kind of research institute in advanced semiconductor and then also MEMS and also. So I just tell you that sorry today I can only give you this online lecture. Yeah, and of course, let me try to show you about that kind of thing for you to have an idea about why Netherlands can do excellent in this area. What do you think? Do you have any idea? Netherlands can has excellent this kind of semiconductor and the sensor. And from my point of view, they have well connect with many leading company and R&D institute. So that I would say is still one of a very good way for Netherlands, although it's a very small country, right? So I don't know. Do you have any idea about what's the population of the Netherlands? The Dutch people, Any idea? Do you have any idea about what's the population of Netherlands? Compared with population of China, What's the population, Any idea? Hong Kong population is about 7 million people, right? And Guangzhou, I think population of Guangzhou city is about more than probably 20 million. And Netherlands total is about 16 million, 16 million people. Smaller than the population of Guangzhou. But they really have done very good R&D and city. I would say small. It's a Netherlands is also very special. That's why they have a unique this ASML. Right? I try to give you this kind of reference material for you to see how ASML can have excellent this kind of using semiconductor, this kind of photoreceptor system, right? One machine is 150 million US dollar. I can show you. This something at least you may want to see how ASML is control the world semiconductor technology. And unfortunately, the whole China, 1 billion more people, we cannot try to make this kind of ASML, this kind of stepper for 5 nanometer, 3 nanometer. So how this 16 million people can make this kind of unique technology, I would say it's worthwhile for all of you to think about. I share with this kind of e-book, electronic e-book for you to see how ASML in the past 20, 25 years can really master this kind of advanced, like a UV, deep UV, extreme UV thing. Unfortunately, the whole China, including Hong Kong, we cannot buy this kind of extreme UV machine. One machine is 150 million US dollar. This is something worthwhile for all of you to think about. That they have their own unique strength, I would say. Yeah. Anyway, I just tell you this is something unique strengths you may want to look into this kind of thing. Why this 60 million people has such kind of unique this kind of way to push this kind of advanced semiconductor technology to the level, and only one company in the world, right? Only one company in the world can make this kind of extreme UV system. It's I would say it's a worthwhile for all of you to learn. Okay, I came here, and of course I visit IMEC. As I show you, IMEC is one of a very special research institute, about more than 5,000 people. So that it's also worthwhile for all of you to have some idea about this kind of IMEC as something. I would say it's unusual. A research institute is in the world. They are making advanced semiconductor device, but unfortunately, they cannot work with any of research institute and company in Hong Kong and China for advanced semiconductor. So that this is based on U.S. government this kind of sanction. I would say that is something it's interesting for all of you to have some idea about this kind of unique strengths of this thing. Okay, anyway, so I just briefly mentioned about part, and last time we'll talk about all this scaling thing. I will not try to skip this part, but of course, I will talk about this kind of scaling law, right? And then describe about scaling law for solid mechanics, fluid mechanics, heat transfer, and also tell you about how to use the kind of dimension analysis, so that I hope that you are able to, I don't know if you try to download that kind of free MATLAB app to see. At least last time I already shared with you about how to use MATLAB to do dimension analysis. And I would say still is one of a unique thing. Please try to give a try. So that is something quite important. And of course we talk about all this kind of scaling and also law, right? And so I think we skip this part. This is what we discussed last time, right? And so last time I think we talked about another quite important thing in terms of scaling for heat transfer, right? Typical for heat transfer in micro scale, right? Of course, we talk about three important heat transfer, right? Heat conduction in the solid, heat convection in the fluid, liquid and gases, and radiation. So this is each of this kind of heat transfer, right? So this is related to heat conduction, right? And the radiation and heat convection. So these are three dominant heat transfer. Of course, as I mentioned, for engineering point of view, so that we try to normalize this kind of heat transfer, right? So H here, this part is related to heat convection, right? And the normalized with heat conduction, and this one is a NASA number, right? So that in terms of practical application, so that the engineer we need to understand, so that you control by normalized velocity and normalized this kind of a Prandtl number. Prandtl number relate to this kind of what's this? What's the physics behind? Any student have some idea? Any for fluid mechanics, we look at the normalized parameter. Right? Rayleigh number is what? Rayleigh number is related to normalization of two forces: viscous force, right? And then normalize this kind of, it's a viscous force, right? Force normalized with this kind of inertial force. This is it. How about this Prandtl number? Do you still remember? What's this kind of phenomena we try to normalize in our UG heat transfer? Definitely, you can see this is related to some of heat transfer. See, heat capacity. Internal energy, right? And then probably it's a thermal mass, right? And this is what this one? K, thermal conductivity. So related to the heat conduction. So basically, this is also normalized. There's two heat transfer, right? And then describe it. So in general, so that in our UG heat transfer, we normalize, try to, is it easier to have generalized the kind of semi-empirical, right, equation or formula. So we are using this kind of semi-empirical equation for design of this kind of thermal engineering. So, and of course, another important thing here we mentioned is a Biot number. So what's Biot number? Actually, it's also related to, it is about the two phenomena, heat convection, heat conduction. So if Biot number is can place with us, how can we try to look at if this system, thermal system, right? You will look at cooling of your CPU, cooling your iPhone, so that can you, if you look at normalized Biot number, and then it can tell you if you can using simplified model, one feeder system, so that you can try to describe this kind of heat transfer, cooling of your CPU. So this is also quite important for thermal engineering. So that I tell you, this is something, it looks like, and then of course, last time we also mentioned, right? So this kind of heat transfer have been quite important, useful for a series of practical technology, including inkjet, right? Inkjet is what? It's the application of a micro, this kind of a heat transfer with phase change, right? Micro heater phase change. You have a micro heater, then you try to what? You try to, with very short period of time, you heat up the ink, and then liquid ink change into the vapor bubble, and then but phase change, then suddenly a vapor bubble will what? Have a rapid increase of pressure, right? And the pressure, high vapor pressure, can use and pump in out of a nozzle. So this is one of, I would say, unique way, right, for my application of micro heat transfer. But basically, this is what is application of a micro heat transfer. With a change from liquid to vapor bubble, and this is a rapid increase, huge the kind of pressure now increase, and then as a driving force for to push this kind of ink now out of nozzle, micro nozzle. So this is I would say one of a unique application of micro heat transfer. In macro scale, can this inkjet work? What do you think? What do you think? In macro scale, can in macro scale, can inkjet work? What do you think? Huh? Any idea? In macro scale, actually, it doesn't work because the level is kind of micro scale heat transfer with phase change and no micro scale, the kind of fluid mechanics. So that once you micro the kind of nozzle, right? So you push this ink out of nozzle and then become this kind of what, liquid jet. So that then, because this kind of competition of this kind of pull force, basically you have some kind of nozzle, right? So that you have certain this ink inside here, and then you have and then you push this out, and then it becomes liquid jet. So this is liquid jet, right? So it's a liquid jet, okay? And then because the hydrodynamic instability of inertial force and the viscous force, so in this case, the liquid continue jet into the what? Become the breakdown into the droplet. So this kind of thing can only work in micro scale, this kind of inkjet. In macro scale, this inkjet doesn't work. But on the other hand, that's why we mentioned last time, if you traditional this kind of a channel, right, we can use a pump for air conditioning system. right? So that but if you micro scale, you cannot using traditional way the micro pump to use in micro scale. So that is something I will tell you. This is the important thing you need to understand why scaling is quite important. Medical research and MEMS for micro heat transfer, why micro heat pipe, mini heat pipe. This is important for laptop computer and even smartphone. Now cooling is so important. Of course, there's another kind of thing, thermal MEMS. Right? If you have a very good this kind of thermal, this kind of engineering to make a micro heater, temperature sensor, you can make a series of thermal flow sensor, thermal motion sensor, right? Thermal thermometer, thermal gyroscope. So that today I told you I will invite this kind of my former PhD student now become young professor in San Yat-sen University. He has been do excellent research in thermal MEMS this kind of gyroscope. So that is something he will give about 1 hour lecture about how we can do this kind of thermal motion sensor. So thermal MEMS motion sensor, including a thermometer, thermal gyroscope, so that based on micro fluid mechanics, based on micro heat transfer. Yeah. And of course, the difficulty of this thermal motion sensor is very complicated. Very complicated, so that if you don't understand the physics behind combination of the micro scale heat transfer, micro scale fluid mechanics, and very difficult for all of you to come with a good design of this kind of micro MEMS sensor. So this part, without very good kind of modeling simulation, it's also very difficult for all of you to come with a very good design. That's the difficulty of this kind of thing, right? Because intrinsically, this kind of micro MEMS sensor is very complicated thing. So that in terms of physics behind, so I just tell you that this part unfortunately is somehow without very good understanding about the kind of micro heat transfer, micro fluid mechanics, and then in the past more than 10, 15 years, there are many research tried going on to make a thermal MEMS sensor, but none of those kind of research in the world can push this kind of thermal MEMS motion can compete with inertial-based motion sensor. So that of course, my PhD student has done excellent job, and then we really demonstrate they can CMOS MEMS thermal motion can compete with mainstream the inertial sensor in the industry, and then we file international patent. Yeah, and that's something you will see. Why at about 8:30, he will give you about 1 hour introduction about the kind of unique thermal MEMS sensor and compare with inertial based sensor. Okay, and that's how I also mentioned about this kind of micro heat transfer, micro channel flow. So basically, it's become more and more important now, right? So with kind of the scaling of a macro channel to micro channel, so in this case, the heat convection or normalized heat convection coefficient, this number can tell you, right? So that if the channel diameter or covariance scale of a micro channel is getting smaller, and then H heat convection would be even better. So this is important for scaling, right? If you have a very good micro channel or array of micro channel, so potentially you can have much better cooling. So that this is you can come with maybe micro heat sink or a micro channel, right, for this kind of cooling of CPU, GPU, and even smartphone processor. Yeah. So this is something I would say important for advanced 3D IC technology in advanced semiconductor. As I mentioned, that if you look at TSMC 3D IC, this kind of team led by Dr. Dok Yu, they really can push the technology and demonstrate there's much better cooling for advanced this kind of semiconductor. Like in the near future, I would say in the near future, your advanced CPU, GPU, AI may have this kind of micro channel for cooling. Yeah. And of course, last time we mentioned a smartphone has a billion or 10 billion of transistors, so that cooling will be important. Yeah. And last time I was mentioning about the kind of issue. Micro heat transfer in general have been research going on for more than 20 years. So unfortunately, so that there's many research tried to going on, and then what's problem? It turns out different research group, they have come with different research results. So the large scattering of experiment data. So why will happen? Huh? Because I would say one big issue is now because if you don't carefully understand the kind of very complicated heat transfer, right, in microchannel or thing, then you how you categorize this kind of heat transfer, right? Combination heat conduction, heat convection, and is very complicated, right? So that at least one of my PhD students graduates in almost 16 years ago, so that try to address this kind of issue, right? So if you're using silicon to do the kind of micro machining, you can make a micro channel on silicon wafer. So what's the problem? Silicon is very good heat conductor. So in this case, in terms of, then in this case, you face some problem to categorize the kind of the heat transfer in more detail. So that that's why I at that time I work with my student to think about how to overcome this problem, right? By try to come with a little bit better design of this kind of micro this kind of channel integrate with micro heater, micro temperature sensor, micro pressure sensor, right? So that in this case, I told you that if using silicon and then a large most of the time you may have some suffer this kind of problem, huh? Suffer this kind of problem. Oh, one student asked why different results still get published. Well, in the early stage, right, when this very good question. The student asked why. Well, in the beginning, more than 20 years ago, so that still there's no consensus, right? If you are the pioneer to do research, the first experiment result, you make a unique microfabrication or microchannel, and then you can publish paper. But of course, then I think one student asked a very good question. Why different research can still publish if you are first one to make a microchannel and then do the characterization, and then 20 years ago, and most likely is nobody have tried to do careful. So then you can publish paper. But also gradually is a lot of people, more people publish paper, and then if you're not the first one to make a second the kind of microchannel, and then so that you can publish paper. But nobody knows your result is good, and then some students say. So this is very important. If you are the first one in the world to make this kind of working silicon microchannel, and then for cooling, and then 20 or 30 years ago, and then I think you can publish paper. You can publish paper, no problem, because nobody know if your result is reliable or not, no paper. Of course, no, there's no problem. But if you have already maybe have 10, 100 paper published, then it's getting more tough to publish paper. That's something I tell you that the thing. Since at this moment, I would say if you Google to find maybe I would say 700 paper, right, published in micro heat transfer, so that it's not easy for you to publish paper now. There's a lot more people have done this one, so that if you're not the first one in the world, then I would say it's challenging for you to publish paper, right? Unless you have unusual technology, have a much better the kind of micro cooling technology, then so things like. So if you try to Google to find this kind of micro channel cooling, what's the thing? How many paper? What's the thing? Now you cannot publish even without very good this kind of research world. And then, so you can see, I just show you, if you set down microchannel cooling, you have 154,000 paper related thing. So if 25 years ago, an easy part paper, but now it's difficult, difficult, without unusual new technology and just like TSMC, there are 3D IC things. So definitely, if you are able to demonstrate you're using CMOS process, right? TSMC CMOS process come with unique 3D IC integration for cooling. Definitely, you can power paper. If you are able to demonstrate using standard CMOS process for 3D integration, then you see. Oh, one student still hasn't. What if following proof the pioneer work is wrong? Then well, anyway, so that that's why you may want to be careful, right? You cannot trust all the paper like published. You have to develop your own very good this kind of now based on fundamental principle. You make a judgment if that paper published is reliable now for you to trust the paper. So the student also asked very good question. If the paper published is something you need to be very careful, right? So cannot 100% trust those paper published. Okay, so that this one student asked this very good question. So what if the following work proved to be wrong? Then so that if you have done very careful research and then modeling, simulation, and then so that then you have multiple solid research work in terms of modeling, simulation, experiment work. Then so that people will trust your paper, right? Your research work. So this is something here. At least I pushed my PhD student 16 years ago. We need to be careful to do design, fabrication of microchannel, the silicon glass microchannel, and make sure we have very, very good kind of experiment work. So here I just show you that we come with this kind of unique microfabrication process from silicon wafer, and then we deposit silicon dioxide, and then patterning, deposit polysilicon and patterning, and then you have this kind of multi-layer, right? Silicon dioxide, like LPCVD, silicon nitride, and LPCVD, this kind of oxide, and then do this kind of multi-layer thing, so that as I mentioned last time, so this also require understanding about the kind of mechanic issue, right? Typically, silicon nitride has tensile stress, and then silicon oxide have a compressed stress, right? Si3n4 nitride, silicon nitride have this kind of a tensile stress, and then SiO2 oxide, silicon dioxide, is a compressive stress. So that and then we need to, in order to make a working device, so that you have to stress engineering, right? Basically here, based on sound mechanics. So if you have very good measurement about the stress of this kind of thin film material, right? Silicon nitride, silicon oxide, and then you can do stress engineering, right? Stress engineering, so that you can make a reliable this kind of microchannel, integrate with microheater, integrate with a micro pressure sensor and temperature sensor. So that is something is an important thing. Here I just tell you so that here you see, and then my PhD student come with another glass wafer, and then you try to do the etching. You can do the wet etching. All right, maybe special kind of chemical wet etching, make a microchannel, and then of course, and then do the bonding, right? Glass wafer bond with this kind of silicon wafer, right? Without kind special kind of another bonding. This also I would describe a little more, right? So that there is additional the kind of application, so that this part needs some special kind of silicon to glass, the kind of bonding, and there's some special thing called another bonding, right? Another bonding basically is try to bond silicon wafer with a glass wafer, but of course, there's additional issue. If you try to buy typical normal glass wafer to bonding, then your second glass wafer will break into pieces because what? Thermal stress. Okay, so that there's some thermal stress issue, right? If you pick up this kind of glass, which is normal glass, you during fabrication, your whole wafer will break into pieces. So that's why for this kind of another bonding, we will require special pyrex glass. Pyrex glass is using from a coning, this kind of Dow coning, this kind of thing. Right? iPhone this kind of display using some special kind of gorilla glass, right, to make a very good kind of glass for iPhone. This kind of glass cover, right? So Coney has some special kind of Coney pyrex glass, which has what? Very good thermal expansion. Thermal expansion coefficient of pyrex glass made by Coney is met with thermal expansion of silicon wafer. In this case, you can minimize thermal stress. If you don't understand this kind of mechanics, and then randomly pick out this kind of material, and then you can never make a working kind of silicon glass thing. So that's why this is something I tell you. There's a require very good this kind of micro machining. It turns out you have to understand a lot more things. Fabrication process require understand about many the kind of mechanical issue, right? Material and mechanical engineering issue, right? Sound mechanics, sound mechanics, thermal stress. All this is something I would say important. Yeah. And then of course you drill a hole, right? And then you can let it inlet outlet, right? To let this kind of liquid go in and for cooling. Okay. And then so that and then you can see we also try to do additional etch back. What happened? Once you make typical thin wafer is about 400 micron. Okay, so that then we etch back here. The thickness of silicon wafer is about typically is about 400 to 450 micron. Okay, so that what's the problem? Silicon is very good thermal conductor. So in this case, in order to minimize the kind of heat loss, right? So that we need to do etch back, right? Etch back thing so that we try to, you see here, we do this kind of etching on the back side. Etching from the back side of silicon wafer. Okay, so that this is also quite critical to make sure you can minimize the kind of uncertainty. You see, etch back so that we try to, okay, front side we have to do protection. Back side we put in this kind of special kind of wet chemical to remove majority of silicon wafer. In this case, we are able to minimize this kind of. This thing is really trying to what? Minimize heat loss. This is also quite see. This minimize heat loss. Heat loss from the heat conduction, right? Via this kind of heat conduction on the silicon wafer. This is one of important way my PhD student 16 years ago to minimize this thing and get more reliable experiment data. So that I just tell you, this is something it looks simple, but you really have to come with very good understanding about all these issues so that you can make this thing and then easy. And then we can use they can doped polysilicon. This polysilicon here, sorry, here poly here is poly means poly means this is a polysilicon. Okay, same thing based on LPCVD polysilicon. Okay, low pressure chemical vapor deposition. Okay, and then so this kind of doped polysilicon can use as heater, and also you can use as temperature sensor and pressure sensor. Of course, then you should ask, how come doped polysilicon you can do this one, and then what how can you, right? Polysilicon, basically it's a dope polysilicon. It's some special doping. It's a dope polysilicon. Okay, as a micro heater, as 10% and percent. How can we do? Oh, that will describe a little more about this issue, right? So that if you want to use this kind of a polysilicon as transducer, and then so that require additional engineering. And here I demonstrate basically, so once you can, this all done in our UST cleaning facility. UST do have a very excellent this kind of cleaning facility, so that so this is a real array of microchannel and array of micro heater, micro temperature sensor per sensor, and then here I demonstrate they can have a this kind of microchannel, and then use SEM, right? Service scanning electron microscope to take a section of this kind of our device to examine if we can really make a working device. Here, this is a zoom up about SEM picture about we have this kind of micro pressure sensor, right, and temperature sensor, and also micro heater, right, and then this additional aluminum wire as a interconnect, so that in the case we can use additional wire bonding so that provide this kind of electrical voltage for heating, and also electrical thing for sensor output. So this give you some idea. But anyway, so in real fabrication, it was much more complicated. And of course, as I mentioned, if you do the pure experiment result, sometimes you may not, maybe you cannot find this kind of very good, this kind of results. So you may need to do additional this kind of simulation and to analyze the kind of very complicated heat conduction and heat convection, so that here demonstrate this kind of additional safety simulation to understand about non-uniform, right? Non-uniform, the kind of non-uniform, this kind of heat, complicated heat transfer, right? Basically, you have heat conduction, heat convection, yeah. So with this kind of simulation, then an experiment result, then you can try to improve this kind of agreement between your simulation experiment and understand about the issue about the thing. And I can give you additional paper, right? If you want to look at more detail about all this research work, not only here, that give you very rough idea about fabrication and thing, right? So I think I can give you the paper if you want really much more detail, right? In terms of microfabrication process and simulation analysis, how you analyze experiment data and generate much more reliable result and compare with even theoretical prediction. So that is somehow, I would say, is non-trivial. But that's why you see, you won't get a very good, reliable research result. You see, so that at least 16 years ago, my PhD student can done excellent research, so we can get much more reliable result, right, and minimize the kind of problem. Yeah, I just tell you, it's in general, it's non-trivial. Okay. Okay, so do you have any question? Of course, last time we mentioned about this kind of microchannel is important for cooling, but sometimes uh, microfabrication may be expensive, so that this professor Pan in Guangzhou come with a precision machining and make a mini channel, and then he done the excellent job. Actually, he has come with another branch of precision machining, right, and are able to make a mini channel, mini heat pipe for cooling of a smartphone and also data center. So actually, he has got the very good research, and then he has a company and make a real product, right, for cooling. So in general, cooling is always a big problem. So that you may want to look into the Professor Pan. From my point of view, he is the one has done excellent research, and he has done also turned the product into the company, and then in Fosan, and then received a big funding to make a real product. So that part, I would say, if interesting, I can give you additional linkage about that Professor Pan's this kind of work, right? And then it's not a research paper; it has tried to make a real product, yeah. And also, last time I also mentioned about another branch, electrokinetic microfluidic device, right? So basically, we mentioned typically you need to make some dielectric material, glass, or some non-electrical conducting, this kind of microchannel. And then if you apply, you have some liquid. Liquid inside liquid is an ion. Ion may be a proton, or ion can be DNA, a charged particle, right? And protein of cell. So in this case, this kind of electrokinetic microfluidic can be used for analysis of for maybe separation of DNA or separation of cell, or analyze the kind of sample from the clinical sample. So this has something, and this Caliber Life Science as the first company make this kind of electrokinetic microfluidic product, and went to IPO, become public company. I think almost 20 years ago. Yeah, and this electrokinetic device has four kind of phenomena, right? Basically, electrophoresis. Electrophoresis is what? Basically, electrically, I can do the separation of some kind of microparticle based on the kind of electrophoretic mobility difference, right? So that this is it. And then, of course, we also have osmosis. Electrically, we try to push the liquid in microchannel as a micro pumping, right? And also we also can do another streaming potential, right? So that in this case, if you have, right, you see, the field created by motion ionized this kind of fluid as a long stationary charge surface, and one more is a sedimentation potential, electric by charged particle. So these are some very unique kind of phenomena in this thing. Of course, we have additional electrokinetic phenomena. Dielectrophoresis. What's this? Dielectrophoresis basically is we're using AC, this kind of electric field, and then electric field, and then so that it's frequency dependent, and then in this case we can use AC to electric field to what? To apply from some microparticle, and then we can either under certain frequency we can create some attractive force. Well, basically you make a microelectrode and applies the kind of AC the field. You can dielectric force. You can use as basically it's something quite important. Dielectric for research basically is using this kind of AC, right? Saying to create some either attractive force or repulsive force. So that in this case, there's a way you can think about try to use as way of the separation mechanism, right? Or this kind of repulsive force. To manipulate this kind of microparticle. Microparticle can be cell, maybe protein, or some other kind of maybe even you may regard as DNA, something. Yeah, this is I would say one of quite important way for microfluidic, right, to do this kind of separation. Okay. And of course, last time we will show you that actually this has been, right, electron osmosis has been used as practical way in micro scale, right? So that once you have an ion in the liquid, and then your glass have certain surface charge, negative charge, and then once you apply large voltage, then you can try to push this one, and then so in this case, then you can have hydrodynamic kind of drag force to push this kind of liquid in one direction, and then you see basically it's voltage apply and then push liquid in one side, so you can use it as a special electro-osmotic pumping in this thing. And of course, sometimes you may need to try to manipulate this kind of electro double layer, right? For control the kind of electro-osmotic force. Sometimes you may control that kind of concentration ion. So debye length scale is a quite important thing, right? So basically, if a glass, if a negative charge here on the surface charge, and then so concentration of ion in the liquid, so that can change the kind of debye length scale that can manipulate the kind of electro-osmotic effect. Yeah. Sometimes you need to want to improve electrokinetic performance of the device. Yeah. Here, last time we show you basically this is two kind of electrokinetic phenomena: electro-osmotic as pumping, right, and then injection of the sample, and electrophoresis as separation of mixture of different microparticle. It can be DNA, it can be protein or cell, or even more common thing. This is last time we just show you this kind of example, and of course people also use this one to separate a mixture of multiple DNA thing. Why? For you see here show you you can microchip electrophoresis separate a mixture of many DNA, 100 base pair, 500 base pair. Or maybe I should give you a thing. This typical 100 BP is what? Base pair. Okay. So one base pair is about 3.4 angstrom, right? One BP is around 3.4. This kind of 0.34 nanometer in terms of size of that thing. So typical double strand DNA is quite small in terms of diameter, but it can have long DNA, right? Human DNA. I don't know if anyone is from bioengineering or CBE, so that how long is human DNA? Huh? How long? How long is human DNA? It's human DNA. Huh? Any people in this bioengineering? At least I told you 25 years ago, I tried to work with this kind of micro and nano electrophoresis. If you look at those lambda phage, right? Lambda DNA is 48 kilobase pair. If you look at typical lambda phage DNA, right? From the bacteriophage is about 48 kilobase BP. Okay, so that if you try to use fluorescent dye to label this kind of DNA, lambda DNA, now it's about 20 to 23, 20 to 23 micron in length. So you have many ATCG put together, so that if you label fluorescent label this DNA, then you can observe the kind of DNA do the separation. Anyway, so this electrophoresis has been useful for this kind of medical diagnosis, and also it can be used for analyze very complicated mixture. Right here, I show you it can be also for agriculture, quality control. Yeah, and people also do this kind of integration. Right, that means you can make this kind of micro fluidic device for process sample preparation of cell from maybe human blood or some sample of maybe from waters, like seawater for water monitoring, right? Cell lysing. Cell lysing means you break the cell into pieces, right? And then you can get DNA from cell, right? Once you have a DNA from cell, it may be if concentration of DNA is not high enough, then you amplify low concentration DNA, and then you can do additional separation of mixture DNA. right? So this is one of a very in the past more than 20, 30 years, people gradually want to make this kind of integration, lab on chip. Yeah. And of course, I told you there's many different kind of micro and nano, the kind of a microfluidic device for DNA separation. Yeah. And that's time I was mentioning another branch microfluidic device is only useful in micro scale, right? Surface tension dominant the kind of microfluidic device. So this is something, and of course, this is based on electrically. If you make a microelectrode, a pair of microelectrode, and apply voltage, you can change surface tension, right? So in this case here, let's demonstrate. So you can electrowetting to electrically can manipulate the droplet, right? And so this is early stage research, and then gradually you have a lot more electrowetting on dielectric, as mentioned. So this is become one of the quite useful, important thing in terms of in the past 20, 25 years. So that basically this can become a series of company to make a real product for electrowetting. Yeah. So basically, so electrowetting on dielectric, basically you apply the voltage, right? And then it charge change free energy on dielectric surface, induce change in the wettability and surface tension. So why we need to have this kind of dielectric layer? Why? Because dielectric layer, most likely with high K material, dielectric, in this case, you can use what minimum voltage to change this kind of surface tension. So that this dielectric layer, I would say, is quite important. We need to use in order to use in order to use low voltage, right? To induce this kind of a force, right? Electrowetting manipulates this kind of force, then we use high K, high dielectric constant material, dielectric material. So in this case, we use minimum voltage to manipulate this kind of droplet. So that is one of important for making more practical device for real product. Yeah. And again, so here I show you in general, you see the theta is this kind of contact angle, right? It depends on the voltage, right? So that this is, that means electrically we can manipulate a contact angle surface tension, and that is quite important. Of course, if you try to apply this kind of DC, then probably it's difficult to manipulate droplet. Then you may need to use in kind of AC voltage, and then so you can try to move this kind of droplet now in different direction. And of course, one of the important things for engineering is we need to think about engineering, because if using some typical material, coating material, those kinds of surface tension may get some contact angle, get some saturation, cause some nonlinear behavior. So that in this case, they may use some additional material and additional coating to make sure minimize kind of nonlinear behavior of this kind of contact angle or surface tension. Yeah, this is also quite important. In general, you have open electrowetting. You only have a the kind of microelectrode on insulation layer, and you have a closed electrowetting. Now, on both sides, you have a microelectrode to manipulate the kind of droplet. And so this is another branch. And in general, of course, if you want to look at details, so that actually we may need to analyze based on fluid mechanics, a droplet, and look at this kind of surface tension, and that we can analyze the kind of based on Young's-Laplace equation to see how I'm going to manipulate this droplet based on electrowetting device. Of course, this kind of thing has been people in the past 20, 30 years, gradually people think about how can we use electrowetting for kind of a portable device to detect second DNA, RNA, or detect COVID-19, detect this anthrax or SARS or COVID-19 or TB. So that how? If you want to detect those kind of COVID-19 or SARS in 2003, what's the problem? Huh? What's the problem to detect the kind of a suspended kind of virus in the air? Do you have any idea? What's the problem? Problem is it's very difficult to the concentration of those virus in the air is very low. So that in this case, it's difficult. If you there's no way, that means you think simply you see sample those kind of suspended virus, right, in the air, and then you try to do the kind of simple preparation and detection, right? So there's a low concentration of those virus suspended in the air. So here, how can you use electron wetting device to the sampling? Hey, this is something require you have some new idea. So basically, one of my old friend, Professor S.K. Cho, right? I had overlap with him at UCLA 25 years ago. So basically, he demonstrated, you see, if you have an electron wetting device, right, and then a Jopley, and then you can try to use Jopley, manipulate Jopley, and then so Jopley has some liquid and contact with this kind of nearby, this kind of suspended kind of air, the virus particle, so it can use as way to sample the airborne the kind of virus or particle. So I would say this is a quite interesting idea, and then you can see Jopley move around near this kind of inlet here, and then you try to capture and those kind of airborne virus can be attached on the Jopley. Yeah, here you see very sophisticated. Right, you have a glass, you have additional or Teflon dilation material. We need to use a very good high dilation constant. This kind of material, high K material. Teflon is one of a good this kind of material. If you standard silicon like a CMOS compatible, then maybe you have to use very high voltage to create this kind of electrowetting phenomena. So they have some engineering this kind of Teflon, and then as a diluted material, and use ITO. ITO is transparent electrode, right? So in this case, that's also quite useful. Right? Basically, use a micro electrode, and then with dilation layer, and then in this case, apply the voltage to manipulate the conserve tension. Yeah. And here, as I show you, so that this kind of idea is not new. One of Felix research lab, Robert Hayes, he do research in Netherlands and published paper in Nature more than 20 years ago. And then his work got attention, and then he tried to commercialize this kind of electrowetting display. And then so that and then he that time he demonstrated this kind of proof of concept device. Hopefully he can replace the LCD, make electron paper. But unfortunately, I think it still takes much more difficult to commercialize. Eventually, this can Vista's company acquired by Samsung, and then but Samsung sold to Amazon, so that Amazon may be interesting about potential electronic paper or their Amazon this kind of Kindle device. Anyway, I told you this is one of very unusual this kind of a device based on microfluidic wetting microfluidic. I would say it's one of quite interesting idea. And here, how this electrowetting make display? Basically, is a you Jopley, right? Basically, if you have Jopley with different color, put some special dye, right? RGB or this kind of CMK or something, right? And then mix so that if light go through and then mix a different kind of color, right? And then in this case, you can make a display. So this is the, I would say, quite interesting way to see how you come with combination of the micro electrowetting microfluidic as a display. There's another branch is electrowetting to lens for smartphone. So Veriodic is a company in France who try to make this kind of a droplet as a lens, right, to control the focal length. As show traditional this kind of zoom lens in the big camera is using very bulky. And actually, if you have chance, maybe you can try to look at our UST library. Library has some special way for you to try to borrow this kind of traditional, like for example, Sony or some Canon, this kind of camera to make a picture or video. So that that is, I would say, you can try to look at UST and then traditional, this kind of a zoom lens is very bulky. So that, I don't know if you have ever tried to use a kind of traditional digital camera. Any of you have tried to use one? If you look at library, you can borrow those kind of expensive camera, digital camera to make photo and video for some of your project. Actually, I went to library and borrow the kind of professional, this kind of camera, and then they do have this kind of thing, but I would say it's it's quite expensive. Yeah. Any of you using traditional this kind of camera, digital camera? Huh? No? None of you? You only use smartphone? Take a picture and also the if you go to library, you can borrow this kind of much more expensive this kind of camera with this kind of a zoom lens. If you go to this kind of CMZ, Creative Media Zone, you can borrow. You can borrow this kind of camera, and then and that actually is quite expensive. But you can borrow. Yeah, for some student they borrow this one, and then the zoom lens is very huge. But the one we just show here, but you don't want your smartphone with very bulky this kind of zoom lens, right? So this kind of droplet base, electrowetting based lens is much more compact, and that is something. And then of course, if you look at Xiaomi, I remember Xiaomi has come with this kind of they call it liquid lens. Actually, it's electrowetting this kind of zoom lens. Yeah, Xiaomi has really used kind of electrowetting for their smartphone. Yeah. Anyway, electrowetting is one of, I would say, quite unique this kind of electro device, and there's a series of company to make a real product for biomedical application, as mentioned, like Illumina, the world number one company to the DNA sequencing this kind of product. So they're using electrowetting to do sample preparation for DNA sequencing. Why? Oxford Nanopore is another company to electrowetting for their nanopore sequencing. So there's a series of companies really try to use this electrowetting to make a real product. So this part is somehow, I would say, it's quite interesting for you to look at a series of this kind of real product. If you look at the Oxford Nanopore, so you will find they really use this kind of electrowetting to the sample, this kind of preparation for the thing. Oxford Nanopore is a nanopore for the sequencing, and then they really have some interesting this kind of electrowetting device to do sample preparation for DNA nanopore DNA sequencing. And actually, they really make a portable nano. I would say this kind of interesting nano fluidic device for DNA sequencing. Yeah, so it's very interesting, technology and product. You can see in the old day, 20, 30 years ago, DNA sequencing required maybe a big room to the kind of sequencing, but now with the kind of nanopore, it's portable nanopore sequencing with electrowetting device. It's quite interesting for all of you to think about. In the near future, maybe the smartphone has this kind of it's interesting for all of you to understand. Microfluidic, even nanofluidic, has reached this kind of maturity. You see a series of products. It's not only for basic research. Okay. Okay. So I don't know. Do you have any question? So that maybe I should try to put this one for all of you. Any question for this part? Okay, nanopore, oxo nanopore really use oxo E for DNA sequencing. So this is I would say one of a unique this kind of application, and especially in COVID-19, there's a lot more this kind of mutants COVID-19 virus. So that I remember some country they really use this kind of nanopore sequencing to quickly do a sequencing of mutant COVID-19 this kind of virus. Yeah. Okay, I think now there's another important part of this thing in this particular one is related to the electrostatic, this kind of phenomena. So why this is important? Because in your smartphone, we have MEMS sensor, right? Using capacitive type of MEMS motion sensor, micro mass spring system, and then we also need electrostatic force as this kind of thing, so that electrostatic this kind of thing has to be used in the your smartphone, this kind of MEMS motion sensor. So basically, when we apply the voltage on a pair of microelectrode, right? This is basically is a pair of microelectrode. Then once apply the voltage, and then you create some electrostatic force. So the key question now is, if your voltage or electric field too big, what happens? If dielectric breakdown. So that in this case, we need to be careful to understand, right? So that this basically this is a P pressure and the gap of this pair of two electrode, and this kind of thing, the breakdown voltage. So that it really depends on your design of this pair of microelectrode, right? And you can see, so that here you can see if you have certain kind of design, and then you find, oh, this is the breakdown voltage. So your voltage apply on electrostatic force for your MEMS sensor should be below this number. Otherwise, you damage your device. Yeah. So this gives you some idea. Of course, there's another application for this kind of dielectric breakdown. You may want to make a high voltage cause some dielectric breakdown to generate some plasma. Okay, plasma is important for our microfabrication. We have the kind of high density plasma divided to S silicon to get a micro machine sensor in your smartphone, right? And of course, there's another. Oh, sorry. And here, let's quickly show you. So basically, for engineer work on this kind of a pair microelectrode for sometimes for electrostatic force, for mass sensor, mass spring system, or electrostatic force for MEMS micromirror. So basically, so you need to be very careful how like engineering design of the gap of this electrode, and then relate to the smaller than this mean free path, lambda or bigger than zero, then there are different kind of behavior. So that this is something I think important for practical design of product. Of course, in this case here, I give you another way, right? So that for different like gases, so that the result may be different because the mean free path is different. So here I give you what's the for different gas molecules, they have different kind of breakdown voltage. Okay, so this also can help you to understand how engineering this kind of electrostatic, this kind of a device, right? And then understand how we try to work on the kind of breakdown voltage. Okay. And so one final thing is there's another quite interesting important thing in terms of dielectric field for electrostatic transducer. Why it's important for a family of many devices, sensor actuator, so that when we use different kind of dielectric material, right? So like silicon dioxide is definitely CMOS compatible, but their dielectric constant is low. If you want to have very low voltage for electrolytic device, or maybe using aluminum nitride, much higher dielectric constant. Aluminum nitride have been used for what? FBAR filter in your smartphone. This is for smartphone, this kind of filter. Okay, so this is a thing, and then hafnium oxide and titanium pentoxide. Oh, with one student. Any question? FBAR, I will briefly mention about some of this FBAR device later. Now, FBAR is every smartphone has 20 to 30 FBAR filter. But fortunately, here we most likely have import FBAR filter from overseas, from United States, from US company, and also Japan. So that it's one of quite important thing. FBAR is something I would say quite important, quite thing, but it's also non-trivial to make a real product. Okay. And of course, as I mentioned, electrostatic, this kind of actuator, it can use using electrostatic micromotor, right? So that you need to be careful about how we can use what's minimum applied voltage without kind of breakdown. Okay, I think we already finished part. Do you any question for this particular part? Any question? No question at all? If not, then we may need to go to the next chapter. So the next chapter is related to transducer. For transducer, basically, we mentioned there's a tool. So here we go to this. This is quite important. Basically, micro transducer, right? So that the transducer can be regarded as some kind of either sensor or actuator. Okay, both sensor, micro actuator belong to transducer, right? So that typically we may also look at this as some energy transduction device, right? And we can classify transducer based on different method, right? So this is something, and here when we look at the energy transduction device, basically, so transducer can be the device can transform one form of energy into another one. That's why both microsensor and actuator is part of transducers. A sensor basically provide useful electrical output in response to specific measurement. Right? It can be input acceleration, become the kind of G sensor or accelerometer, or input this kind of angular velocity become gyroscope, while input pressure become the pressure sensor. While actuator, you can think about actuator, for example, we mentioned what electrostatic micromirror can become the TI, tensor instrument digital micromirror array. So this is actuator. Okay, but anyway, it typically is a conversion of those kind of energy between electrical to mechanical or electrical to other kind of thing. Okay. And of course, there's all kind of different energy when we look at the transducer design. But of course, we will not cover every aspect of this kind of energy for transducer. But typically, we mention about electrical energy, magnetic, mechanical, radiant, thermal, biochemical, and these are very common things for us to discuss. Okay. And of course, when we try to look at the classification of different transducer, so either we can look at transduction principle or measurement. What kind of thing you measure? The input, pressure, acceleration, gas concentration, and pressure. And what kind of fabrication using this kind of thin film, ceramic, thick film material, semiconductor, or RC. And application. This kind of transducer can be used for automotive, medical, aerospace, or consumer smartphone. And finally, we also make this thing about this in related to if I able to what able to look at this one based on this kind of low cost or high performance, this kind of sensor. Well, I do say that's also quite important. Sometimes we need to be careful about cost. Why? Smartphone definitely is something low cost, but the volume is big. RC. Okay. One student asks if servo motor is one kind of actuator. Yes, of course. Yes, okay. So motor, right? Motor is what? Motor basically electrically, we try to apply electric energy and then make some rotation, mechanic output, right? Rotate some rotor. So basically, this kind of motor, right? Motor basically is one transducer, actuator, one type of actuator, right? Basically, electrical input, right? And then mechanical output based on rotation, right? Rotation of this kind of rotor. Well, okay, so this is good. We have a student, it's important you not only listen to our lecture, but also understand what we discuss here. Yeah. And of course, we sometimes we also describe about this kind of the three type of transducer in terms of this kind of thing. One thing is modifier. You have input energy, or modify this one and output energy, or input energy with cell generator output energy, or input energy with modulation. And these are a little bit different. So here I show you cell generator. For example, your photovoltaic solar cell, and then tachometer or piezo mains, right? And thermocouple, LED, this is a cell generator. Piezo mains, right? So that basically is a piece. For example, you have a mechanical input, generate electric output, or electrical input, generate from mechanical output. So piezo mains. For example, last time we show you this kind of X mains. X-Men is one example about real product for this kind of advanced, that kind of very compact, this kind of main speaker. So this is, I would say, one of interesting piece of man's product made by the company in Silicon Valley. Let me see. If you look at the X-Men's, I think I'll show you last time so that it's, I would say, interesting this kind of like man's actuator, because I would say in the before not too many this kind of company can make this kind of piezo MEMS actuator. So I would say it's interesting to show you. Interesting. Oh, very compact. VR, AR, a headset, VR, AR, MR, three-dimensional, hi-fi, sound. Very compact with 7 SMT, with ASIC circuit. So you can really put into your this kind of earphone. And three-dimensional hi-fi. Wow, very robust. Well, this company is doing a very good product now for real this thing. So that I believe they are doing a very good job. And actually, this company's piezo MEMS speaker, according to my old friend, the nation I know is made by TSMC. So TSMC is not only make us like CPU, GPU, AI chip for your iPhone, but also make this kind of MEMS, this kind of actuator as product. So if you have a chance, you may want to look at thing. I think that they are trying to like several days. They have a special day in Shenzhen, Shanghai to show this kind of piezo MEMS device. So anyway, so this is I would say this is one of a unique the kind of generating cell generating piezo MEMS device as actuator. Okay, and of course another branch is modulating the kind of transducer. Strain gauge. So what's strain gauge? You have input strain and then resistance, right? So once you have a larger you kind of they can stress strain and then you trend this kind of resistance, right? So that modulating the resistance change, right? Thermal resistor, LDV, LCD, these are the modulating this kind of transducer. A modifier, for example, transducer, thermal radiation detector, and the thing, heat flux detector. Okay. Anyway, this is give you some interesting way to describe the kind of transducer. And of course, another way to describe the kind of how classify transducer in terms of sensor actuator. Sensor basically you have a different kind of input, right? Mechanical, radiant, thermal, magnetic, chemical, and then convert into this kind of energy into the electric energy, right? It's sensor. And then we have a physical sensor. I think we mentioned why a microphone, MEMS microphone become quite important for our new smartphone. Every smartphone now have a lot more this kind of microphone. And why? Why your smartphone needs so many? 1, 2, or 3 or more? Any idea? Huh? Why smartphone need a lot more this kind of MEMS microphone? Any idea? Why? Any idea why smartphone need a lot more? Any idea? Because you see, if you want to have very good the kind of smartphone, and when you're talking, and then you want to have very good kind of noise reduction, right? And then so once you one microphone, then you cannot optimize the kind of directionality and also sensitivity aspect ratio. So right, so you can see, so in case once the array of microphone and then micro sensor array, you can easily do additional the kind of software engineering to adjust the kind of sensitivity, aspect ratio, and noise reduction, so that nowadays all the new smartphone, iPhone have a lot more 1, 2, 3 sensor. Oh, Alexa, remember I show you the kind of Alexa smart loudspeaker, also about 6 mains microphone array. So this is a quite important thing. Mains microphone array cam is important for all the smart device, for smartphone, smart this kind of loudspeaker, like Alexa and see. How do you say? Like Alexa, this kind of made by Amazon Alexa. Okay, so these I would say become quite important now for all the smart device to improve the performance. Yeah, and here I show you basically there's a noise cancellation. When you use your smartphone on the street, there are many noise, right? From the bus, car, and many things, so that you don't want, when you're talking, there's a lot of noise. So once array of microphone, and then you get noise cancellation, right? And so this has become quite important. And in the old day, typical microphone is using condenser microphone. Traditional microphone is still okay, low cost condenser microphone or electric microphone. But unfortunately, what's the problem? Traditional condenser electric microphone is okay 10, 20 years ago, but it's not okay now. Do you understand what's the problem? Traditional electric microphone has been used for, still you can find some product, but what's the problem? Traditional, the kind of not mains microphone. The problem is traditional microphone product. They have no the kind of ASIC chip, like ASIC, this kind of chip to amplify the signal, right? So that but now you have a lot more. All the smartphones digital electronics, so you need to have very good kind of mains and this integration. You say mains micro integrate with ASIC chip, so this become quite important for all things. Anyway, so there's a series of different technology people can make this kind of microphone. For example, piezo resist high microphone, why basically you have this kind of diaphragm, and then you have some doping on some silicon thin film material, right? And then you can make a piezo resist microphone. This is one possible way. And of course, people also make a piezoelectric microphone or electric microphone. Again, this is one of the most mature product for many years. And 10, 20 years ago, most of mobile phone use this one. But again, the problem of this one, no, it's very mature technology for many decades. But it cannot. The problem is it cannot be integrate with those ASIC kind of a chip for this kind of a smartphone. For you see, as I told you, if you have 1, 2, 3, 4 more this kind of mains microphone, then you can minimize the kind of additional circuit, right, in the smartphone PCB board. So that's become one of it. That's why now we have a lot more smartphone using kind of mains microphone, because they allow have much more the kind of a digital interface, right? Here I show you this is a series of product, like North is one of pioneer in this kind of mains microphone company. So this is Sonic mains microphone, okay. And so that here I show you with AC. AC is a company, the headquarters in Shenzhen, next to Hong Kong. It's a Hong Kong public company. It's one of the top 3 in the world to make low-cost, high-performance microphone for those top smartphone company, iPhone, Samsung, even Huawei, Acoustica, and a device, and more. Yeah. And here I show you, in order to have very good this kind of MEMS microphone, again, not only you have a good this kind of acoustic knowledge for MEMS microphone, but also ASIC chip. Okay, so this is quite critical for real product. Without this kind of very complex design, then you cannot make a good, reliable product. This is an X-ray image about real, those kind of MEMS microphone in your smartphone. And of course, if you look at more detail, so that you need to understand the MEMS microphone design in terms of acoustic, right? So how the microphone work? Do you have any idea? How the microphone work? Basically, you have some very flexible diaphragm. Your flexible diaphragm, the silicon wafer, right? This is some thin film material. And then, of course, you also need what? Additional this kind of hole here. So you allow that kind of pressure fluctuation. I would say it's AC pressure. Acoustic basically is a pressure, a function of time. And then acoustic pressure will acoustic pressure, right? Basically is acoustic pressure will try to cause some what? Deformation, like a loading or deformation of this diaphragm. So in this case, so then you input the acoustic pressure and it causes a deformed diaphragm, and then if you maybe use capacitor or piezo tie and then convert into electrical output, right? Then you have electrical output, right? As this kind of microphone, yeah. And anyway, this MEMS microphone has been a lot more. The application, smartphone, or maybe smartwatch, Apple Watch, and all this kind of digital camera and even computer, laptop computer, and thing need this thing. And even I told you this kind of Apple's is AirPod. They have a MEMS motion sensor, MEMS accelerometer with MEMS microphone arrays in your smart earpod. So it's I would say quite important thing. Yeah. And of course, let me show you there's another branch, right? There's a lot more this kind of physical sensor. So that here. So here, and I show you is another branch of a physical sensor is inductive sensor. Inductive sensor basically is using electromagnetic kind of principle. So if you have magnetic field, and then you have a coil, and then if you have a voltage, electric current goes through, and then based on Faraday law you learn in physics, so that the induced electromagnetic force will proportional rate change of magnetic flux to the loop. So once you move, right, you move this kind of, you have certain kind of motion, and then velocity, and then you generate some output voltage. This is way you can make inductive this kind of sensor. Right? This kind of sensor has been used for in many industrial applications. For example, you can use in measure certain kind of thing for vibration, thickness of the thing, eccentricity, and part recognition, and I think this is industrial sensor have been used in a series of industrial application in the manufacturing plant. Yeah, I think it's quite important. Of course, you see, there's a lot more I can use for industrial the kind of manufacturing process. Now I show you there's another branch of this kind of proximity sensor, so that in now many of smartphone like iPhone, they have this proximity sensor. So what's this? Proximity sensor basically in your smartphone, iPhone, basically you have detect two things. One detects the kind of the distance, another detects the kind of light intensity, so that the distance between the user and your thing. Basically, these proximity have been quite important for every smartphone to what? Save energy, because your smartphone consumes a lot of electricity, right? You limited kind of battery kind of electricity. So the use proximity sensor basically is trying to make sure, right? If you're using the smartphone, then maybe you adjust the light LCD display. If you don't use it, put on the table, and they will try to maybe turn off your display for energy saving. And so, of course, here there's another interesting. So that in order to make a better kind of prime sensor, actually iPhone, Apple tried to use a 914 nanometer. The what difference here is here. So it's more infrared, so that when you try to share, you don't your eye, human eye, the user to look at that infrared light source, right? So this 940 nanometer turned out to be much better to make sure have a better user experience. So that you say, so industry like Apple really spend a lot of time to make sure user interface, right? Here I will show you also quite interesting. The kind of iPhone 10 or beyond, the interesting facial recognition. So what's this? Actually, iPhone 10 has STMicroelectronics near infrared sensor using SOI wafer. Okay, so the near infrared for what? Not only one point sensor. You look at basically you have using array of like a solid laser V cell, right? 300 laser array, right? And with kind of special kind of DOE. I think we mentioned one before. And then you have 30,000 dot, right? Laser dot illuminate your face for very resolution, and then using kind of infrared, right? For this thing. Basically, you can see so that if you try to look at the iPhone 10, so you have a RGB camera, near infrared, the infrared camera with DOT, a thing, right? Anyway, it's a quite sophisticated kind of thing for all your smartphone has a 10 to 20 sensor. So this is definitely is I would say getting much more sophisticated kind of sensor design. And of course, you see, it's also quite competitive. So the typical iPhone, you have a typical RGB. Sorry, I made a mistake. It's RGB. Typical camera or similar image sensor, and you have additional infrared camera and AOS. So what's this? Another light sensor in some smartphone, ambient light detector. Let me show here. It's also quite almost AOS, ambient light sensor. So basically, you have a proximity sensor, right? For energy saving a smartphone, AOS, ambient light sensor. So it actually it can as a way to adjust the kind of LCD or GAN LED display to improve the performance of the display of your smartphone. Okay, and here I show you there's a you see the series of this kind of company. They are making this kind of module, right? RGB camera or similar sensor. Sony is #1 in the world, and Samsung Korea #2, OVI #3 in the world. And then we have a proximity detector from STMicroelectronics in Europe, Philips, VCell, solid laser, and TI. And then we have a dot spectrum illuminator. Okay, AMS, another important kind of sensor company in Netherlands and Austria. So they are very strong a branch in Netherlands. Okay, and then we have an ambient light sensor and AMS. Anyway, so I just tell this give you some idea about real product. And then now I'll show you there's another branch about basically transducer. I show you have it's considered of sensor and actuator. Why? Typical input transducer is sensor, output transducer is actuator. I think typically, as I show you, we have many input, mechanical, electrical, or maybe thermal input, and then co-sound sensor and electric output, right? And then you may need using some kind of thing process you maybe your smartphone and control some actuator, maybe loudspeaker or something, yeah. And then of course, sometimes we also try to classify transducer based on this kind of different kind of transducer. We have thermocouple, pH sensor, meter, LED display, LCD coil, metal resist sensor for conductor. And basically, you see, so there's an interesting meter index to think about how you have an input and the output, and then is any modulation thing. Okay, so this gives you some of the interesting way to classify the transducer, sensor, and actuator. And of course, one more way to classify transducer is how we try to, as I mentioned, right, input-output response, so that how you try to input as some kind of energy, while mechanical energy, output maybe electric energy, right? So these are the way we describe, classify transducer. One final way is we do the what? Based on energy principle. So if you look at the thermodynamics in our UG mechanical engineering, we actually look at energy principle, right? So that in this case, we may try to look at the one transducer, right? So that you involve certain kind of energy, maybe this kind of some stress strain, yeah, pressure, and maybe voltage, electric, and magnetic field, and even this kind of temperature and entropy, so that once you look at this kind of energy principle, differential energy of that transducer material or device, and then you can try to analyze this thing for practical application. Of course, another thing, scaling of microtransducer, so that of course, as I mentioned, we deal with those main sensor between millimeter 10 to the power minus 3 meter to 1 micron. This is typical our main transducer, okay? And this will be close to the size of a blood cell, bacterial, and human kind of a hair. Yeah. And here, typical our physical microsensor, if you look at all the kind of energy transduction, right, from electrical, mechanical, magnetic, radiant, thermal, then in general, combination of these 5 types of energy, you may find, oh, we have a large number of different kinds of possible combination, right? It may have some 350 this kind of energy coupling, right? So that something I would say is one unique kind of thing. And here I show you one of the interesting thing, the kind of you see here one example of a Motorola integrate silicon pressure sensor. You still have this kind of silicon diaphragm, and then a pure micro machine, right? And then because you have additional transduction principle, right? To input this kind of pressure. Basically, you have input pressure, and then cause some deformation of diaphragm, solid mechanics, diaphragm, and then cause some diffraction. Basically, your W diffraction maybe function of X, Y, Y, C, and then once the diffraction, you change maybe resistance or capacitance, right? So in this case, you can try to measure output. Maybe you could output electric output. Okay, so this is a typical way. Now, of course, in reality, for real product, you need to have an ASIC chip, right? Low noise amplifier, chip with ADC or things. These are typical important things. And of course, another branch is the kind of actuator, right? So this demonstrates electrothermal actuator, right? Electrical input and what? Create some stress. If you have BIMOL, two layer of this kind of thing apply, and then maybe different layer, different thermal expansion coefficient. If apply electric energy, cause some thermal stress, and then you can cause some deformation of this micromirror. This is can be one of the kind of a way it is electrothermal actuator control some this kind of mirror. Okay, finally, let me quickly show you this another quite important. I don't. Do you have any question? Any question? Because sometimes I think we already talked about too much. Any question up to now? No question at all? At least I would say we find one student as last question. I hope that it's important. You not only listen to the lecture, but I do hope that you should try to have digest what we discussed in our lecture note and saying not just listen. Right? If you have a question, please try to don't be shy. You have to ask question or here. Yeah. Any question? No? No question at all? Then we try to now once you have certain kind of sensor, we just quickly show you what's typical important this kind of performance of sensor. Typical we care, right? As for research R&D in the beginning, we care about first is probably sensitivity. How sensitive is your sensor, right? You want a highly sensitive sensor, right? But normally, highly sensitive sensor may be quite expensive. And dynamic range, I want to measure the kind of input, maybe temperature or input pressure in acceleration. So it has wide dynamic range, right? So these are important things. And then if your sensor is linear, nonlinear, these are quite important. And sometimes we also look at reliability, repeatability. So in real product, actually, a lot more to be into the real product. In the beginning, most likely in the research stage, I would say sensitivity, dynamic range, and this one would be critical. And gradually, if you show your sensor have an SM performance, then you care about the other secondary performance of sensor, right? So that this is a typical way for doing research here. You see, but unfortunately, in many the kind of sensor, most likely is difficult to have 100% linear sensor input-output response. So that in this case, what we should do, and we categorize linearity, right? Input from very small 0 to certain thing, and then your sense output may be nonlinear. So in this case, you categorize this kind of linearity, right? As way, this is a difference of minimum to output, maximum output here, and this is the input, right? Maximum input and maximum minimum input. So this is a way to define this kind of linearity. The second thing is how the dynamic response. When you want to look at the transient response, time-dependent measurement of temperature or acceleration or something, then we may need to understand how fast maybe temperature sensor will be changed once you have changed about maybe temperature. When you do the boil water or something, right? Maybe look at your CPU, GPU, AI chip, right? You generate a lot of heat. So how you try to quickly to measure the time dependent temperature response. This can be important in some area. And of course, another thing, sometimes, for example, you use a MECH motion sensor, you can characterize as a mass spring system MCK model. So that in this case, we care about dynamic response of this kind of sensor response. So in terms of simplify this kind of ODE, ordinary differential equation or transfer function. And of course, when we look at our sensor design, sometimes we look at electromechanical, for example, MECH motion sensor. So that sometimes we may want to convert mechanical mass spring system into what equivalent circuit model. So in this case, we can try to analyze the design for this equivalent circuit model. So ECN has been widely used in our MECH this kind of research, sensor research. In this case, typically, I would say, I think it's one of the quite important. We may, for example, mass can be corresponding to what? Inductor. And this kind of spring related what? Spring related to the capacitor. Spring. Okay, and then what? Damper. Damper relate to what? In mechanical system relate to this kind of resistor. Okay, so this is a typical analogy. Okay, so the typical analogy between mechanical system and mass spring damper system to electrical this kind of equivalent circuit model. Yeah, but of course, this kind of analogy is not unique. Sometimes you may use different way to define the kind of MCK, mass spring damper to LCR. So this is somehow, I say it's not unique. This is a inductor. Why? This is a capacitor. This is resistor. It's not unique. Sometimes they use different way to look at the electromechanical analogy. And of course, this is another thing, so that when we look at transducer parameter, actually we also care about saturation time, rest time, and a lot more sensitivity and other things, right? Maybe temperature coefficient, the drifting problem. Okay. One more issue is when we try to make our sensor, MECH sensor, we may want to look into the kind of the problem. If you have certain kind of nonlinear input response, you can think about how you linearize the kind of input response. Okay, so this is compensation, right? Static error, and sometimes you also need to do the kind of feedback. You have a sensor, and then if you want to make a milling or billing of sensor, so that yeah, major uncertainty in microfabrication process. So you may need really kind of a MECH sensor with the kind of closed loop feedback. In this case, you can what? In this case, you can minimize uncertainty by closed loop. The kind of feedback, the kind of sensor design can increase the robustness, of this kind of MECH sensor, right? Because there's a lot of uncertainty in fabrication process, so that robustness, you just say, especially you want to make a milling of or even billing of sensor, so that you don't want every sensor the input result different, so that in this case you can use this kind of feedback. This one to tune this kind of uncertainty in your microfabricated sensor. Why? Maybe it's simply like a resistor R. You tune this resistor, and then with the kind of closed loop feedback, then you get much more reliable the kind of mass production of the MECH sensor. Yeah. And of course, sometimes you may also need this kind of a compensation. based on the UG control system principle. And this is typical, right? So that if your open loop, this kind of main sensor has certain limitation, right? You can use the kind of UG control system principle to design this kind of compensator, right? To improve this kind of the performance of this main sensor. So as mentioned, and your smartphone, iPhone, you have very sophisticated the kind of main motion sensor with the closed loop feedback. Right? Is it in every smartphone? Yeah, for mains accelerometer, main gyroscope. Yeah, and here this is an example, right? As I mentioned, so that so this is one of the classical example, ADXL50, right? Annual device company, they make the first surface micro machine, the kind of mains accelerometer for automotive industry. And so they not only have a mass spring system and capacitive, this kind of sensing, and then we have the additional feedback, right? And then so that in case it makes sound much better, this kind of product. And I think we almost, in general, when we look at this main sensor, in the beginning, we look at device level, sensor actuator. Sometimes, if we want to make a more practical device, and then we make a sensor system or transducer system with additional interface circuit, controls, signal processing, and I/O, so that typically we may look at sensor system or this kind of main transducer system. And so your sensor have, or actually can come with some special interface circuit, right? And then these are components to improve this kind of transducer's performance. Yeah. I think we almost run out of time to fishing, so that I may not be able to continue this part, but I also need double check about if Huang is out, he's on this kind of Zoom meeting now. So I don't know. Again, I think I don't want to spend too much time, but again, so this is a very brief now talk about this kind of introduction to transducers, right? And, so in the following about 1 hour, I want to ask Huang, my former PhD student, become young professor in Sanyang University, to give the kind of mains this kind of gyroscope in terms of inertial and thermal type. He had done excellent research to make a come with theoretical model about thermal, this kind of angular rate sensor, and theoretical modeling, simulation, and dual fabrication, and even the optimized CMOS main thermal accelerometer. So that I think I need to pass this one to Huang to give this kind of for him to give this kind of guest lecture. I don't know if we again. Do you have any question up to this for my 2 hour this kind of lecture? Any question? If now I should pass this one to Huang. I will try to make sure you can be a co-host for me. Okay, so I think probably that's it for my part. So if not, then I will let the Huang to continue this kind of guest lecture. Huang, are you ready?
Hello, Professor. Yeah, I'm ready.
Yeah. Okay. So that
Okay, let me
can
share
you
my
share your
screen.
screen? Yeah.
Let me share the screen first. Can you see my share screen?
Yeah.
Is it okay now?
Yeah, can you also turn on your microphone? No, the camera.
Oh, okay.
Camera, so that at least
is it okay
I
now?
would say okay.
Yeah,
Okay.
I already turn on the my camera, so it's okay.
Okay.
Can you see?
I will try to remove spotlight and for you to become this one. Yeah. Okay, yeah.
Okay.
Yeah.
Can I start now?
Okay, now it's your turn. It's your turn now.
Okay, thank you, Professor Lee. And hello, everyone. My name is Huang Luo, and today is my great honor to be here to give a guest lecture. So today here, I would like to share with you something about MEMS gyroscope. As Professor Lee mentioned, it includes two parts. One is conventional MEMS gyroscope, and another type is the thermal-based gyroscope. So first I will start with the conventional MEMS gyroscope. So MEMS stands for microelectronics mechanical system. So MEMS gyroscope is a sensor that measures angular rate of rotation. And in the past years, gyroscope has gained popularity for use as rotation rate sensors in commercial products like mobile handset, automobile, and game console. I believe some of the students may play the game with your mobile phone. So one popular game is PUBG. In Chinese, it's called 和平精英 or 绝地求生. So I think you may some of you may try this game before. So during this game, I think you may tune the motion of your body so that so in the game your view can be adjusted automatically. So this is based on this MEMS gyroscope. And the working principle of the MEMS gyroscope is shown in this slide. As you can see, in the x-axis, the proof mass is driven into the oscillation. So there is a vibration in x-axis, and due to the presence of the rotation in z-axis, it will induce Coriolis force in y direction. This induced periodic Coriolis force will cause the vibration, the oscillation in y direction, and this oscillation in y direction will change the capacitance in this MEMS gyroscope structure, as you can see from this animation. So we can divide the MEMS gyroscope into two parts. One is the driving mode operation. As you can see here, this is a driving mode and the function in for x-axis oscillation. We use MCK model, mass damper spring model to show, as you can see here. And the second mode is the sensing mode operation for the induced oscillation in y direction. And here's the equation. And this here I list the common criteria for the MEMS gyroscope, including performance and the specifications. For the performance, it includes measurement range, sensitivity, nonlinearity, etc. And for the specification, actually we care more about the cost of this type of sensor, because we actually the final goal of our MEMS guy is to fabricate the sensor with low cost but high performance. So we care more about cost. So I put the cost as the first specification here. Of course, there are other type of specification for MEMS gyroscope. And another type of actually motion sensor is MEMS accelerometer I want to introduce here. Is the working principle of MEMS accelerometer is a little bit similar. As you can see, when there is no input acceleration, there's no movement of this solid probe mass. But when there is input acceleration, there is a movement of this mass to cause the change of the capacitance. As you can see in this animation, it stands it is C1 and C2. So this change of capacitance will cause the output electrical signal change and this output signal, electric signal change can be associated with the input acceleration. The reason why I show the MEMS accelerometer here is that we can combine this MEMS accelerometer with the MEMS gyroscope to be a MEMS motion sensor. And here is a table I list here about the comparisons of different commercial MEMS motion sensor. Of MEMS motion sensors includes the gyroscope and accelerometer, as I showed before. And here it includes the different performance, measurement range, sensitivity, and also the price. Here is the example of MEMS motion sensor module actually I used during my PhD study. It's a commercial one I bought from Taobao. And here on the left-hand side is the parameters of this sensor module. With the built-in battery for power supply, this sensor have two kinds of connection way. First one is use this USB wireless connection to connect the module with your PC. And another type of connection is use the mobile phone app through the Bluetooth connection, and we can monitor the sensor the output data through this Android mobile phone. And I can show you a video about this sensor before I do the testing. I did the calibration. You can see when we move it, rotate it, we can get the corresponding output data in our computer. Yes, so this MEMS sensor module can capture the motion of like our body. And this is another testing with this sensor module. I put it on the rotation platform with a stable input rotation. We can measure the angular rate, on our smartphone. So combined with a lot of other types of MEMS sensors, MEMS gyroscope, MEMS accelerometer can be used for smart construction machine, at least here. We can see in addition to MEMS motion sensors, there are other types of MEMS sensors like temperature sensors, speed sensors, etc. So this is a very important application for MEMS gyroscope. And another important application is relevant to Professor Lee's project about using the MEMS IMU MEMS motion sensor to monitor the pine driving process. You can see when we penetrate this pine into the ground, so this will cause some uncertainties like vibration and tilting angles. So we'd like to use this MEMS motion sensor to monitor this process. As you can see here, if we put our sensor MEMS our sensors into this pile, we can realize the real-time monitoring about this pine driving process. And based on the data analysis and feedback mechanism, we can tune the parameters during this pine driving process. And here, and also I'd like to introduce another applications about the structural health monitoring with MEMS sensors. Also, these applications should be realized with different type of MEMS sensors, including the MEMS gyroscope, accelerometer, and others like temperature sensor, humidity sensor. And for the structural health monitoring, I want to show you an example. Actually, here is the Timma Bridge in Hong Kong. As you can see, there are many different types of sensors used for structural health monitoring of this bridge. They use different type of sensors. And here is the structural health monitoring cost. And this is another example about structural health monitoring. It's a Dubai tower. And here is I just use a table to simply summarize the information of different structural health monitoring examples. We can see as time goes by from 1997 to 2008, the cost of structural health monitoring decreased a lot. Each year, the structural health monitoring cost decreased by around 15%. So it's actually this kind of cost decreasing is realized by the mass production of the MEMS sensors. And in the previous slide, I just show you the examples of the structural health monitoring. And so this means that the structural health monitoring is important. If the structural health monitoring is not well realized, or is not if this kind of monitoring is not good, then bad things will happen, as you can see here.
As you can see, this bridge was exceptionally long and narrow, over half a mile long, only 39 feet wide.
The high winds
it lasted just 4 months.
1940s.
During construction, we see 8 feet tall, which were supposed to stiffen the bridge against bending. However, some up and down vibration was observed during the entire useful life of the bridge. Here's opening day.
The bridge is well built.
On November 7th, the bridge suddenly went into a
see
twisting motion. The wind speed was a steady 42 miles per hour. This was enough to keep the bridge oscillating in one of its natural modes of vibration with a period of 5 seconds. A professor of engineering went out to see what had happened. He's coming back, walking with some difficulty along the nodal line, which is the center stripe of the roadway. It's remarkable that the girders were this flexible. This is photographed at normal speed. However, a collapse was inevitable after a little more than an hour of this. The car had been abandoned earlier. No one was injured in the whole affair. However, a small dog in the car was frightened and was afraid to come out, and he perished along with the bridge. The bridge was rebuilt using a stiffening truss instead of girders. The new bridge is completely stable.
So we can see that if there is no good design for the bridge and no reliable structural health monitoring, something similar will happen in different places. Another similar examples I want to show you is about the Humen Bridge in Guangdong, China. As you can see, this unusual vibration of Humen Bridge on May 7, 2020. This kind of vibration is similar to the Tacoma Bridge, as I showed in the previous slide. So through these two examples, I want to show you the importance of MEMS sensors to monitor this structural health. And the reason behind this unusual vibration actually is the von Karman vortex 3. This von Karman vortex 3 is relevant to Reynolds number. And as the Reynolds number increase, we can see from this animation, the von Karman vortex 3 will appear. You can see the Karman vortex 3 will appear like this. This kind of von Karman vortex 3 shedding will induce the vibration of the bridge. It's just like apply a periodic lateral force on the body of the bridge to cause the vibration, as you see in the previous videos. So this is the reason. The final state of the von Karman vortex 3. Okay, in the past slides, I showed you something about the about MEMS gyroscope and its applications. So starting from this slide, I'd like to show you something about thermal-based gyroscope, which is also my research topic during my PhD study. As you can see in this slide, there are many different applications of gyroscope, including the inertial navigation system for aircraft, motion controlling in robotic industry, and motion sensing in consumer electronics. So, but the conventional gyroscope, as I showed in the previous slide, actually are costly, bulky, and fragile. So by contrast, thermal-based angular motion sensor or thermal-based gyroscope are much simpler, less costly, and compatible with CMOS process. Usually, a thermal-based gyroscope works on convergence of mechanical variable to thermal variable, and finally to electrical signal for the omega detection, the angular rate detection. Generally, a thermal-based angular motion sensor consists of heaters and temperature detectors. The diagram in this slide here shows the signal transport principle of the thermal gyroscope. The rotation, as you can see here, the input rotation will cause the variation of heat transfer mechanism so as to induce the temperature difference between the temperature detectors inside the thermal gyroscope. And this temperature difference will be converted into the output electrical signal. So according to the different mechanism the thermal gyroscope can be characterized into 3 types. The first type is based on the jet flow. Although it can achieve very high sensitivity because of the enhanced force convection, the structure of this type of gyroscope is too complex, which greatly restrict the miniaturization. The second type of thermal gyroscope it relies on an external acceleration to create free convection. So there will be a serious coupling effect between this external acceleration and the detected rotation rate. The last type of the thermal gyroscope are based on thermal expansion, which shows more advantage than the others. So this is also my research topic. As you can see here, my research topic focus on this thermal expansion-based gyroscope. So unlike the conventional gyroscope, this thermal gyroscope shows much simpler structures by replacing the solid proof mass with the fluid medium. Generally, as you can see in this figure, it consists of 2 heaters here and 2 temperature detectors. The thermal expansion flow is generated by alternatively heating and cooling these 2 heaters. So we can see from this animation, when there is no input rotation, the thermal flow will expand and move symmetrically. So the temperature detectors on left and right hand side will sense the same temperature, resulting in 0 output of the temperature difference. While when there is the input rotation, the induced release force will distort the previous symmetric temperature profile. So as a result, the temperature difference can be detected and then associated with the input omega. So without very complicated structures, this type of sensor is easy to realize the miniaturization and achieve high shock resistance. Also, the thermal gyroscope will be less costly because its fabrication process is compatible with CMOS process. So the mass production can be achieved. So according to the fluid mechanics and heat transfer, we first built the 2-dimensional model for the design analysis of thermal gyroscope. So instead of solving the nonlinear partial differential equations of the fluid mechanics and heat transfer, we use this lump element method, as you can see here, to describe the behavior of thermal gyroscope based on energy conservation equation. So in this model, most of key parameters have been captured, including the input angular rate, sensor dimension, and the temperature-related variables. And through the numerical calculation, we can get the temperature profile from the model, as we can see from the left figures. So the temperature deflection due to the induced release force is clearly demonstrated in this result. It usually takes around 20 seconds for my computer to get such kind of result based on the proposed 2D model, which is much more efficient than a CFD simulation. And here the right figure shows the predicted sensor output as a function of the input angular rate, which shows a good agreement with the experimental result from the published paper, with a maximum error of around 8%. So this shows that our proposed model can predict the sensor output and can be used for sensor design and optimization. In addition to this result, we also conducted a parametric study based on our 2D model to investigate the impact of some key design parameters of the sensor performance. Here, the first result is about the effect of sensor dimension and the distance between heater and temperature detectors. We can see that the optimized distance exists in both X and Y directions to achieve the best sensitivity. As you can see, the peak in these two figures. Especially a larger sensor length can in X direction can cause a smaller optimized normalized distance between the heater and temperature detectors. Also, we study the impact of other design parameters, as you can see from the right hand side, including the thickness of the heaters, the heater width, and the cavity depth. The predicted thermal output from our model is then normalized with the overheated temperature, as you can see, and plotted as a function of the Rayleigh number. Here, the Rayleigh number is a dimensionless number and is related to the input Coriolis force and the thermal properties of the working fluid of the thermal gyroscope. And we can see from this figure that this thermal gyroscope reviews linear response behaviors in this specific range, in this red range, as you can see. And the nonlinear range can be observed when the Rayleigh number is beyond this range, namely the blue range, as you can see in this curve. So a critical Rayleigh number can be identified from this figure to differentiate the linear and nonlinear response regions for the thermal gyroscope. And the right-hand side, the figures on the right-hand side shows the normalized input-output response of the thermal gyroscope with different gas and liquids, which shows that the different fluid can be used to optimize the sensor performance. Here shows the fabrication and package of the thermal expansion-based gyroscope, and we can see the fabrication process is shown at the left figure. It mainly consists of here 5 steps in this process flow, and the process starts with the growing of the low-stress nitride and silicon dioxide, and the platinum thin film is deposited and patterned by the leave-off process. In the final step, the deep I and xenon difluoride etching are used to release the bottom silicon substrate. The fabricated sensor chip with two heaters and 3 pairs of temperature detectors was embedded into the PCB and wire bonded with the aluminum wires. And we can see an ABS cover was used to seal the chips to form a chamber filled with the working fluid. And here is the pictures of the prototype of our thermal expansion-based gyroscope. And the left figure shows the whole view of the experimental testing setup, according to including the laptop that we use for data collection, the digital functions signal generator, DC power supply, Arduino Yun, and a servo motor controller, a motor, and a Wi-Fi router. And the right figure here shows the more details about our sensor module. It consists of the package chip with the bonding wires, and this is the readout circuit on PCB, and the Arduino Yun board we use to collect data and generate the PWM signal to drive the heaters. And under this white cover, it is a portable DC power supply for Arduino Yun board and our sensor. And all these parts are put on the rotation platform with the step motor. And this is the rotation platform. And through a Wi-Fi router, we can connect the our sensor module with the laptop wirelessly. So the data collection is realized through this Wi-Fi router, as we can see from this video. When we rotate this sensor module, the output data from the sensor can be wirelessly transformed to our laptop. You can see we can collect the output voltage of our sensor through this Arduino monitoring window. So this is the experimental result of our thermal gyroscope. For each group of data under a specific input angle rate, we collect more than 100 data points. And here is the final result about the input and output response of our thermal expansion-based gyroscope. We can see the sensitivity of our sensor is around 0.4 millivolt per degree per second, and with a nonlinearity of less than 0.1%. The experimental result is then compared with the prediction result from our 2D model. We can see from this figure that the sensor response is well captured by our proposed 2D model, with relative errors of less than 6%. So this validates that the model is a reliable tool for sensor design optimization. And based on this experimental validation, the model analysis also shows a good agreement, which also shows good prediction that a larger sensor output can be obtained based on the optimized distance. We can see here the optimized distance between the heater and temperature detectors. And we also did the tape out to fabricate the thermal expansion-based gyroscope by using CMOS MEMS technology. Here, the sensor chip is based on TSMC 0.18 micron 1P6M process. And after receiving the sensor chip, we did the post-processing in our FF HKUST to etch the oxide with the metal 3 layers used as hard mask, and then to use deep IE and xenon dipolarize etching to release the bottom silicon substrate to form the suspending structure. And the thermal gyroscope fabricated by CMOS MEMS technology shows a sensitivity of around 0.1 millivolt per degree per second. So this shows the feasibility of developing the thermal gyroscope with CMOS foundries for mass production. So by extending the previous 2D model with the consideration of ambient temperature effect and working fluid thermal properties, we also developed an integrated ambient temperature compensation method for our thermal gyroscope to effectively improve the output stability and accuracy, as shown in this slide here. The compensation algorithm is predicted by our extended 2D model, and then is adopted into an Arduino open source MCU in an experiment to compensate the sensor output. And the response of our thermal gyroscope at different temperature before and after compensation are shown on the right hand side. And we can see the temperature compensated thermal expansion based gyroscope under this compensation method shows an excellent temperature insensitive output, as shown in the figure here. Temperature insensitive output with a maximum variation of 1.88%, which is greatly reduced compared with the uncompensated counterpart, the upper figure, as you can see here. So this the drifting of the sensor output is effectively improved by this compensation method. And we also did do the optimization with the sensor structure to improve the sensitivity. Traditionally, the thermal gyroscope is designed with the heaters perpendicular to the temperature detectors. We can see from this upper figure. So here we propose a novel design for the thermal gyroscope by employing the heaters parallel to the temperature detectors. And the dominant superiority of this novel design is the sensitivity improvement without increasing the chip area and the power consumption. So according to the analysis, the theoretical analysis and experimental testing, this kind of structure can enhance the sensor sensitivity by more than 65% compared with the conventional design of the gyroscope. And we also performed a systematic study of PWM frequency effect on the sensor performance, including the experimental testing and the time-dependent analysis with 2D model, as you can see from this figure. And the generated PWM signal was used to drive these drive the heaters to induce the temperature difference under the input angular rate, and the detected temperature difference was then converted into the output voltage. The experimental data under different PWM frequency was collected by Arduino MCU to identify this optimal PWM frequency, which can be validated by the calculated thermal time constant from our proposed 2D model. So after getting more experimental data, the result was summarized as a generalized phase diagram, as you can see here, with the normalized sensitivity plotted as a function of PWM frequency and the distance between heater and temperature detectors. From this figure, we can identify an optimal region. In this region, the normalized sensitivity is more than 0.95, and the sensor sensitivity can be improved by more than 10% compared to the previous work. So this research outcome would be very useful to guide the design optimization of the thermal gyroscope. So the final part is about the further improvement of sensor sensitivity. So based on the previous optimal regions and the normalized input-output characteristic of reading number, the thermal gyroscope packaged with the working fluid of SF6 was developed to enhance the sensor performance compared with the conventional nitrogen-based thermal gyroscope, as you can see in this slide. And we can see the sensor sensitivity can be significantly improved. Can be significantly improved by using SF6 as the working fluid instead of nitrogen. In detail, the sensitivity of the SF6 based sensor is 1.56 millivolt per degree per second. This sensitivity actually is more than 3.5 times as large as that of the nitrogen-based thermal gyroscope. So this is the work we did for this thermal gyroscope. So yeah, that's it for my presentation. Thank you, and you're welcome to ask some questions. I don't know if you have any questions. You can open your microphone to ask some questions, or I think you can type in through the windows. What kind of hard mask do you use? I don't know what do you mean by what do you mean about this hard mask for photolithography or for dry etching process? dry etching. Okay, I understand now. For dry etching process, I usually use the photoresist as the hard mask to protect the pattern. But for the deep IE etching, actually I use silicon dioxide as a hard mask. Yes. Because you may know that during the deep etching, the photoresist is not very reliable. There's another hard mask. Yeah, in CMOS type, the hard mask is different. Let me show you here. Yeah. In CMOS type here, yeah, M3 means metal 3-layer. Actually, it's aluminum. It's aluminum. I use aluminum metal layer as hard mask to etch the oxide. You mean the thickness of this metal M3 is 0.5 micron. 0.5 micron for metal 3 layer. No, actually this, because I use CMOS foundries to fabricate this sensor. All these for each layers, the material is not realized by me, but by the foundries. I just did some post processing in NIFF. But I'm not sure they use sputtering or evaporation. I guess should be sputtering. Thank you for your question. I saw maybe you are doing fabrication processing in NIFF, so I think I found that you know many details about the fabrication process. Okay, I got it. So any other questions or any other question from other audience, other students? No questions? Come on, don't be shy. You can ask questions, or you can contact me by email. If you have other questions, we can have further discussions after this course. Yeah, sure. So if no questions, I think probably let's see for my presentation and for my part. I don't know if Professor Lee is here. If I can use aluminum oxide. Actually, I don't have this experience to use this material. I'm not sure. I cannot answer this question, sorry. Maybe you can try, but I guess silicon dioxide is more reliable, or you can use silicon nitride. Yeah, I guess silicon dioxide and silicon nitride will be reliable as hard mask for dry etching instead of aluminum oxide. I see. Yeah, you are considering about the stress, right? Yeah. Yeah, this is a critical issue actually during MEMS verification. You can try. I remember in our NFF, we have this facility to measure the residual stress. You can use a dummy wafer to do some testing. Yeah, and you can compare the residual stress issue between these two types of material and select one type you want. I don't know the name of this machine. No, I only know the principle is based on Stoney's equation. You can ask Li Hou, Hao. You can ask him. He know. Yes, you can ask Li Hou for help. No, ask him to teach you how to use this machine to measure the residual stress. Yeah. Yeah, residual stress. This machine is used to measure the residual stress. And Li Hou is in charge of this machine. No problem. So I don't know if any other questions. No question. I think maybe let's see for my presentation and my part. I think this is also the end of this course, right? Almost 9:20 p.m. 是了 Are you there?
Yeah.
I don't know. Is it the end of this course or any other?
Professor Lee said ends in 20 and this class ends in 9:20.
Yes, I think almost the end of this course.
Yeah.
Okay, thank you everyone. Bye bye.